So let's talk about this for the case of dynamics, where now there's going to be some acceleration. Everything is going to be identical as to when there was no acceleration. We're going to want to write our forces in their x and y components, and now we're going to say the same thing. Sum of forces is equal to mass times acceleration. Sum of forces is equal to mass times acceleration in the y direction, only now a is not equal to 0. So again, all this really comes down to is setting up the free body diagram, and then we can apply these two laws to solve these problems. So if we consider an apple that is in free fall, it's going to have its weight downward, and that is the only force that belongs on the free body diagram. What we don't want to do is we don't want to draw the weight downward in addition to the mass times the acceleration in the y direction. This one is not correct. This one, you could say, I know that the acceleration is in that direction, but we can't make this acceleration touch our free body diagram. The reason for that is because we're going to write the sum of the forces, in this case is going to be equal to the weight, and we're going to say that that's equal to the mass times the acceleration. And if we drew our free body diagram like this, then we would have the weight plus the mass times acceleration is equal to the mass times the acceleration, and again, that is not right, because then we would say that the weight was equal to 0. So if I consider a case where there is straight line motion with a constant force, here I have my sailboat. It's got its weight in the downwards direction, or sailboat, ice boat. It's got its normal force in the upwards direction, and the wind is now blowing in that direction. So I write the force of my wind in that direction. The net force in the y direction is going to be equal to 0, right? It's not going up or down. In the x direction, I would write what are the sum of the forces in the x direction. That's going to be equal to the force of the wind, and that's got to be equal to the mass times the acceleration of the boat. So the acceleration would be in the x direction. On my free body diagram, I draw my acceleration right over here. Now, in the previous example, what if we consider a little bit of friction? Well, still in the y direction, we just have the weight and the normal force. The sum of those is going to be equal to 0. And we have the force of the wind in the positive x direction, so it's going to be accelerating, and it's going to be moving in that direction. And the frictional force, let's now consider a little bit of that. The frictional force is always going to be in the opposite direction as the velocity. So we would then introduce a frictional force right here. And now when we went to write the sum of the forces in the x direction is equal to mass times the acceleration in the x direction. That's going to be the force of the wind minus the frictional force. And if we knew what these guys were, then we could solve for, say, the acceleration of the boat. If we consider an elevator that is moving downward but slowing to a stop, we say, alright, here's my elevator. It's got its weight in the downward direction. That's the mass times gravity as well. And then it has the tension force going upwards, and it is slowing to a stop, moving downwards, so it's got some velocity in that direction. The acceleration must be in the positive direction. So we can again say the sum of the forces in the y direction, mass times acceleration in the y direction, is going to be tension upwards minus the weight in the downwards direction. And again, we can now go ahead and we can solve for, you know, tension if we know the acceleration and the weight. Another way to look at the same problem is if we consider a woman that is standing on a scale in the elevator, and we know that the mass of the lady is 50 kilograms, and the elevator is moving with decreasing speed, so we know that the acceleration of the elevator is in the positive direction. Now the book actually tells you some positions, and it goes ahead and it calculates the acceleration. I'm just going to use that acceleration here, and it says, you know, what is the reading of the scale going to be? So to do this, let's look at all the forces that are on this woman in the elevator. Downward, she's going to have her weight, which is going to be mass times gravity. And in the upwards direction, she's going to have the normal force, which is given to her by the scale. And at the end of the day, this is what the problem is asking for, is what is that normal force? What is the scale reading? So what we would do is we would do what are the sum of the forces in the y direction. In the positive direction, we're going to have this normal force, and in the negative direction, we're going to have her mass times gravity, simply the weight, and that's going to be equal to her mass multiplied by the acceleration of the elevator. So we can write the normal force is equal to the mass multiplied by the acceleration in the y direction plus gravity, or 50 kilograms multiplied by 2 meters per second squared plus 9.8 meters per second squared. And we're going to come up with 590 newtons. Now her weight should be 50 times 9.8, which should be what, 480 newtons, 490 newtons, something along those lines. So because the elevator is descending, but with the acceleration in the upwards direction, she feels heavier, and the scale is going to weigh heavier. And you've experienced that if you've ever been in an elevator that is speeding up or slowing down. Most likely you have. So if we want to look at the acceleration down a hill of a toboggan, and we want to draw the free body diagram for the people in the toboggan, we have their weight in the downwards direction, and then in the upwards direction all we have is the normal force. So it makes it, in this case, convenient to choose our x-axis to be in that direction and our y-axis to be in that direction. And then what we can do is we can break the weight up into its components in the x and y directions. So here we would have the weight in the y direction, here we would have the, over here we would have the weight in the x direction. So we'd say the weight of the toboggan in the x direction, you know, using similar angles, is going to be, let's see, that angle right there is going to be alpha. So that's going to be the weight multiplied by the sine of the angle, and then the weight in the y direction is going to be the weight multiplied by the cosine of the angle. Now if we look strictly at the y direction, we know that the toboggan is not going to bust through the bottom of the hill, and so it's not going to be accelerating in that direction. So we have the normal force going up, and then the weight in the y direction going down. These two forces are going to be equal. Now, in the x direction, I have the same, or all I have is some acceleration going on that is due solely to the weight of the toboggan in the x direction. If before you were wondering why I rotated my axis like this, it's because if I chose my axis in the up-down direction, well, I know that the acceleration is going to be along the direction of the hill, so my acceleration would kind of be in that direction. So I would have a component of my acceleration in both my y and in my x. Now, yes, that is doable, but is it easier? No. So now I can go ahead and calculate out normal forces, and most likely we'd be solving for acceleration. Same as before, there is no force mass times acceleration that belongs in problems like this, where before I was talking about up-down. Same if there's up-down, left-right. We can draw our acceleration along an axis, but it does not belong on the free body diagram connected to the body. So now let's look at two bodies that have the same acceleration. If we consider, a milk carton on a food tray, and I'm applying a force to that, we can work this problem in two ways. We can work on it using separate bodies, or we can look at it in composite. And what I mean by that is I treat the carton and the tray as a single body. So I'll do that one first. If I draw the free body diagram for my carton plus my tray, there's my carton plus my tray. In the downwards direction, I have the weight, which is again going to be the weight of the tray plus the weight of the carton of milk. They're being supported by the table, so the normal force is going to be, in this case, equal to the weight if I do my sum of forces in the y direction. And then here I have my force that is being applied to them. It's going to be 9 newtons. There's nothing else in the x direction, so there must be some acceleration in the x direction. Now this is useful because I can calculate the acceleration of everything as a whole, and we know that these guys are kind of being forced or stuck together, so this acceleration can be applied to each individual body. I can also look at this in separate bodies, drawing the free body diagram first for the milk carton and then for the food tray. For the milk carton, in the downwards direction I'm going to have the weight of the carton, and in the upwards direction I'm going to have the normal force supported from the table, and in the y direction these are going to cancel each other out. And then the carton is being pushed by some force of the tray pushing the cart, and the carton is going to accelerate. If I look at the free body diagram for the food tray, starting off with the weight of the tray in the downwards, the normal of the table in the upwards, again canceling each other out. Here I have my force due to the hand, but resisting that, because it has this milk carton in the way, there's going to be some force of the carton on the tray, and the force of the tray on the carton and the force of the carton on the tray are a action-reaction pair, so they're equal in opposite directions. Still, at the end of the day, I can apply this acceleration to either one of those two guys and solve for the force of the tray on the carton, which would also be the carton on the tray. Now, I can also look at this in two different directions, and in this case you'll have a lab kind of similar to this. Here we have a mass that is being pulled downward and it has its weight pulling it downward, which is again going to be mass 2 multiplied by gravity. It's being supported by some tension in the string, and let's just say for a second that there's not any friction on this apparatus whatsoever. So in your mind's intuition, you would say that this guy must be accelerating in that direction. Now let me draw the components on this mass right here. The only thing that we have acting on it is going to be the tension in the string. Therefore it must be accelerating in that direction. So I'm going to put 2 and 1 here, and I'll put 1 and 2 here just for a little bit. It turns out that the tension in the string is an action-reaction pair, so the tension in the string must be equal to the tension in the string, and also the acceleration of these two blocks is going to be the same. That's actually very useful because we can use information that we determine right here. Suppose we knew this mass and we knew what gravity was, we could find out what the tension in the string was or the acceleration and apply that to the cart up there, perhaps to solve for the mass of that cart if we knew what the acceleration was. So frictional forces, when a body is sitting at rest or whether it's sliding on a surface, it's going to have a frictional force, and that force is going to be always parallel to the surface, and I'm always going to say it's going to resist motion. What I mean by that is if I have some velocity in that direction, my frictional force will always be in the opposite direction as my velocity. Now, where friction comes from is at any surface-to-surface interface. Really, it's not as smooth as I might draw on my pictures. Really, surfaces, they're kind of jagged. And how much friction there is kind of how jagged or maybe grippy surfaces are. And this is interactions between the molecules on the surfaces. The two types of friction that we're going to talk about is going to be kinetic friction and static friction. And kind of the key is, to using these two types of friction is to figure out which type of friction you want to use when you're considering your frictional force. So kinetic friction acts when a body slides over a surface, so it would be when something is moving. Now we write the kinetic friction force, F sub k right here, to be equal to mu sub k multiplied by the normal, where that is the normal force, if you consider your mass times gravity being your weight in the downwards direction. You have your normal force in the upwards direction. That would be right here, and that kind of makes sense in that how much friction is involved in a process depends on how massive an object is. Right? You see tractor trailers, they don't slide as easily as cars when they're on snow. They have a lot more normal force. U sub k is a coefficient that describes kind of how slippery or jagged a surface is, or grippy it is. Static friction acts when there is no relative motion between the bodies. So if you consider a box and you're trying to apply a force to it and it doesn't move because it's a stubborn box, it has a force of static friction in the backwards direction, so not moving. Now the static friction can actually vary between 0 and its maximum value. It doesn't necessarily have to be a single value, because heck, if you push on a box with a given amount of force and it doesn't move, and then you go ahead and you push on it now with twice the amount of force, Well, the frictional force, if it doesn't move, can rise to meet that challenge. So that's why we write the static friction to be equal to, or to be less than or equal to some coefficient of static friction multiplied by the normal force. Now, the coefficient of static friction is not the same as the coefficient of kinetic friction. It is actually larger. And if you think about it, if you're pushing and trying, if you have a box and you're trying to push it and push it and push it, once you get it in motion, it's easier to push than it was when you were trying to get it in motion. What that's saying is this static friction is coefficient of static friction is going to always be larger than the coefficient of kinetic friction. Once you get it moving, it moves very easily. And you can kind of see that graphically here. If you consider a box that is sitting on the ground and you apply some tension to the string and it doesn't move, and you apply even more tension to the string and it still doesn't move, you're increasing and increasing and increasing your force, the force of tension, and then the force of friction is rising to meet that challenge. At some point it breaks free, and we have the static friction, the maximum value for the static friction. The kinetic friction, because mu sub k is always smaller, is going to be less. The amount of force that we need to overcome friction is going to be less than the maximum value of static friction.